Yes. Could you start, Dominique, because we're running out of time.
Okay.
Excuse me.
I will go a bit faster. Yeah. So we speak about digital manufacturing, especially then for the CNC machine case. Next slide, please. So this is just a little overview. What do we understand under digital manufacturing? So I will show you some slides. This is from TWI. So it's mostly aiming at the yellow marked things, which we will also address today, which is about improving quality, cost savings, and time to market reduction. So that's a bit the general ambition of this kind of digital manufacturing. Okay, next slide, please.
I hope this works. This doesn't work.
So what you see here is from, we are there, McKinsey, where you have different digital technologies. On the left, you probably recognize already blockchain, but you also have human assisted by robots, for instance, AI in the middle, and then to the right, some advanced production methods, which are mostly the most relevant for today. And in the bottom, you see the claimed, let's say, contributions or benefits from these technologies, mainly addressing productivity and downtime reduction, productivity increase, of course. And on the right, you see costs or quality, cost of quality improvement, and then also accuracy improvement. Next slide, it will be indicating that these two things are the focus of this presentation. So let's say better productivity, less downtime, and better quality at a lower cost. Next slide, please. This is another slide. You probably know already a little bit about digital twins. This is from General Electric. These are other things you can do with digital twins. It's mostly about reliability, showing what's happening in your process, basically. In the middle, predictive analytics, and on the right, health monitoring. So this is a bit out of the scope of this presentation, but I show it just to make clear what's the difference. And then the next one from Siemens. Next slide, please. Sorry, this is first from Boeing. So you see here a virtual, at least, assembly plant for an aircraft. But more interesting, on the left, you see what they want to implement in this kind of factory of the future, which is AI, of course, robotic automation, and IoT data analytics. But more interesting or relevant for today are the vision systems for quality control. So automated, better quality control, and digital twins for process optimization. So when you push next slide, Miranda, we will see this highlighted. So these are the most relevant things for the presentation of today. This has been implemented by the company Orcaline at Boeing. Next slide, please.
I'm sorry, Dominique. Technique's not working.
We can continue with this slide. Yeah.
Okay.
This is a bit the final introduction. So this is of Siemens, where you see in the bottom right that digitalization is basically affecting everything. This will come back also immediately. So you see a digital twin of the product and the real product, and a digital twin of the production or the factory and the real production. So this is, of course, the core idea of twinning. But more importantly, it shows that everything is digital, not only the product, but also the production. And if you can push next slide, we go to the left here, where you see that the most important sectors are automotive, aerospace, basically, and manufacturing in general. So what do we want to do as Flanders Make at KU Leuven is, let's say, setting up a fully digitalized product production cycle and covering the whole, let's say, part of design, prototyping, production, quality control, assembly, use of the product, and even recycling. This is commonly known as so-called end-to-end digitalization. It has been introduced in other sectors. A very nice example is banking, for instance. You all know that your bank is getting more and more virtual. and that your data are more used by that bank to give you a certain offer. So this is a very nice illustration of coupling all data to have a higher productivity and in the end also more income for the bank. Of course, we should never forget that. Why is this so important? Because digitalization is of course costing money. You need sensors, you need data storage, you need better communication tools, so that should return some value in the end. So that's why we try to cover that in the full production cycle and product cycle, as will be shown. We use virtual models, but it's very important that these models stay synchronized with the real twin. So it's the digital twin and the real twin. So that means that we need sensors in our physical systems. We can also assist, of course, human workers, not only in the factory, but as you will see in this case, in the work preparation and in the design phase. And there is a lot of knowledge in companies, experienced people, where there is a lot of knowledge we can harness through the use of AI that will be also addressed in the very end of this presentation. Next slide, please. So this is the picture we use in our labs. So all labs of Flanders Make at KU Leuven work around this kind of concept, where you see basically, it's in an infinity symbol, but it's basically the product development cycle. So that's not so special. Next slide, please. What we will illustrate today is that we use digital information mainly from the production cycle, in this case, to generate value in other parts of the development. So first, number 6 is the product process validation. So that's basically affecting the work preparation. 8 is basically quality control, dimensional quality control based on these production data. And then you see 4 completely at the left. So this is in the digital phase when the product is not yet made. We also give tools to improve the design. So to give the designer tools to do a better design based on those production data. Because it's a common problem that many companies face, is that the design and the production are typically different departments, and that the more data you get from each other, the better you can make your product, and in very many cases also cheaper. Next slide, please. So this is some more details. I will talk first about physical, where do we get the data, and then on the left 2 virtual cases, but in view of time, perhaps we better next proceed to the next slide immediately. So what we first do is collect data out of a production cycle. So what you see there moving is the virtual and the real machine. So the physical twin of a manufacturing process and the digital twin. This is based on data we get out of the machines. So we read out all the encoders and all other data available from the machine controller. So that's part 1. Second, we move to the left of this slide. We use a sensor. You will see it on the next slide to measure the cutting forces. It's integrated in a tool holder. That's a bit too fast, Miranda. Perhaps we go back. Yes, no problem. So that sensor is collecting the cutting process data, which you can say you can get this also from the motor controllers, but we want to be as close as possible to the process itself to have the highest quality of data. That's why we measure the cutting force in the tool holder. Then we combine this information. The principle is very simple. If you know where the tool has been cutting, you know where the material is gone. Where the tool has not been cutting, there is material left, and that's then the real dimension of your part. But of course, the machine is subject to dynamic effects, thermal deformations. So for time being, we mainly include the machine loop stiffness and the tool stiffness, not yet thermal deformation and so on. That also means that we have a digital model of the machine, including the machine dynamics, which has been identified, in this case, by a hammer test. We also work to improve that in a kind of in-process testing. If we have all this information, we still need to calculate where the material has been removed. For that, we use a very fast material removal model. Why does it need to be fast? Because we want to know the result at the end of the machining cycle. And so if we have the result after the machining cycle in, let's say, little seconds, we can immediately make a geometry estimation. And now we can move to the next. So this is the tool. It's basically a standard HSK tool holder with very high sampling frequency and also very high resolution. So we have multiple samples per cut, and it's completely wireless as well for the power as for the data transfer. So this is just something in a tool magazine which is connected through Wi-Fi to the machine controller. Next, please. Yeah, so this is the real one, only the picture is new here. We can move on. So here you see a first machining result. So we measure the force and all the digital twin data of the machine. And based on that, we do a material removal model based on the original cut of the part. Yeah. And then we can apply this to compare the, let's say, nominal part from cut to the real part, which is then machined. That's what you see on the left. Now I have to say that for this machining test, the Z-axis compensation of our machine was not working. That's why you see a lot of red in the bottom, but on the next slide, this has been solved and you will see a better result. It gives you an idea of, let's say, the raw information coming out of the machining cycle, which is a color plot basically indicating what are the dimensions or the deviations from the nominal dimension of a certain part. Next, please. So here you see a picture of our equipment on the left, and on the right we define the kind of test part with features, common features like a pocket or a circular pocket, and then some straight slots in full or half immersion. So the yellow is in full and the red one is in half immersion. We can go to the next slide. So what you see on this slide is again the reference part on the left in small. This is the nominal part. Top right, you see that color plot again, where we see the deviations from the nominal part. And then bottom right, you see deviations per feature. So the first one is perhaps the most important. It's the green one, number one. It's the circular feature. And you see the simulated dimension, I have to say, which is very close to 22, but 12 micron too small. And if we measure it on a coordinate measurement machine, a high accuracy coordinate measurement machine with basic uncertainty of half a micron roughly, you see that it's 18 microns too small. So there is about 6 micron difference between our estimate and let's say the measurement on a CMM. For linear dimensions, and then we speak about the pockets and the slots, it's much better. There we are close to 1 micron deviation between the CMM and then our estimate based on machining data. So for F2, that's the yellow slot, you see that we estimate it to be 5 micron too small, and the CMM gives 6 microns. So there we are typically within 1-2 microns accurate, leading to an overall, let's say, error of 4 micron, but perhaps that's not the best figure because you see that for linear dimensions, it's much better than for circles. Next slide, please. Now we move a little bit to the left because the technology I just showed you, you can also use for other things. Note that what was before is on the physical part. It's in the machining department. What I will show now is where we use these same data in the design department where the part is still virtual. Next slide, please. So you can imagine that if we have a digital twin of the machine, we can run a machining cycle also virtually. So we just sent the CNC program of that part to the virtual machine tool with all the dynamics included. And that basically means that we have then a virtual dimension of the part. Without reading everything what's on the left, you can see on the right a window meant to be an app in your CAD system, where you see the red dotted lines are the tolerance limits you put, for instance, on a drawing, and the blue line is what you will get out of the machining simulation. So you see that we are asymmetric in the tolerance field. The part will probably be a bit too large. Of course, this is also related to the speed of machining. That's why you see there the green window, which is the material removal rate as a general measure of your machining speed. So if you reduce that, it could be that your blue line goes more to the middle, that you, let's say, go more to the middle of your nominal tolerance field. Another option could be that you change your tolerance or that you change other things in your design. The important message is that you can do this while the part is still not made. So before it's, let's say, a problem in your manufacturing department, you could try in this way to avoid already the problem, especially, of course, for the most critical dimensions. For, let's say, standard dimensions, most factories know what they can produce, so there it's not really aiming to do this for everything, but for where it's critical, this allows you to also check the machining stabilities to avoid chatter that can also be included in this tool. Next, please. Yeah, it's just the same, let's say, but now we also only use the virtual machine. And then the last part, but this is rather new, it's just starting up. So we all know that there is a lot of knowledge in the work preparation in a factory, which is typically a manual operation, although in, let's say, modern machine controllers, you have already a lot of pre-programmed features. So what we want to do here is having an AI-supported CAD/CAM tool. This, let's say, research on computer-aided process planning, as it was called in the 90s, has been done, but mainly based on a kind of scheduling of operations without including, it was more an expert system. What we want to add on that is that we use AI to capture the existing knowledge in a factory, and perhaps it's also a bit depending on the tradition in your factory. So it's not necessarily that every company will make the same work preparation. So that are all things we want to add on, let's say, a kind of computer-aided process planning system as it has been tried before. But the problem with expert systems was always that they have difficulties in learning and that the data after some years are outdated. So we want also solve that second problem. So that's in short. I think I'm still in time. We can conclude by the next slide, I think. So this is again that first picture, why it's infinity, you can ask, because there is even more possible than what I was showing you today. If you push the button again, Miranda, sorry. And again, so this is what we were discussing today, work preparation, design support, and metrology. If you push again, you will see some extra arrows. So you can, based on your production data, also take decisions when you specify the product or when you do the operations and maintenance of your factory, or even when you need to buy new machine tools. You could use those same data out of the production cycle. So it's not necessarily to focus only on number 7 here, the production. You can also do that for all the other numbers. The message is, if you have everything digital, you should try to connect all these design phases as much as possible with mutual data to improve everything as much as possible, because digitalization, as I said before, costs money. To give another example, you can use your car location system to drive, to use Google Maps or whatever. But you can also say automatically there was a pothole in this road, in this location, and you should repair it. Of course, there is a problem of sharing your data perhaps in that moment, but it's just an example that with one system, digital system, you provide information to other systems. With a mobile robot, you can provide data for the maintenance of your factory. That's another example where you can, let's say, with one data set, generate more return of investment. And then we can go to the conclusion. Are there any questions? And you see my contact details there in the bottom. Thank you for your attention.
Well, I hope everyone can hear me. Are there any questions? Let me see. There we are. Are there any questions? There is not much time left, but if you can send your questions using the chat function, we can send them in later. Yes, there are no questions so far. And that's a good sign, I guess. If there are any more questions after this session, you can send it by email to Dominique itself or himself or to me, and we will answer them afterwards. We will send this presentation within a few days for anyone who would like to see it again. And we will thank you for your presence and wish you a very good day. Thank you.
Thank you also from my side. Bye-bye.
Thank you.